All right, everybody, welcome back. So, last time I was talking to you, we were talking about chemical bonds, like what they are, what they do. I mean, it's pretty basic, guys. What they are is they would hold atoms together, right? They are what bond chemicals, atoms together. Yeah, and basically they store energy, they hold stuff together. What else is there to know? Oh yeah, electrons are transferred or they're shared, or there's others. There's actually a third category that we talked about a little bit. Which I'm just gonna call them the weird chemical bonds. So what I want to do for today, I guess now that we know that a chemical bond is what holds atoms together, it contains potential chemical energy. Um, we're going to talk about one kind of bond, which is when electrons are transferred, right? I mean, like I said, we've got three kinds. Electrons are transferred, that's one kind of bond. Electrons are shared, that's another kind of bond. Then there's the weird bonds that just sort of stick some things together, and they're called ionic bonds. So let's just get started, man. Do you want to just dig right into it? Because I kind of do. I don't want to talk anymore. I just want to learn about bonds, chemical bonds. All right. So the first thing we're gonna look at, first thing we're looking at today are these guys called ionic bonds. Now, ionic bonds are formed by the attraction between oppositely charged ions. And I think, my friends, the clutch word here is ions make ionic bonds. Right? Okay, it shouldn't be too much of a mental stretch. So I know you guys get this. So basically what happens is, if you have something like this here, the cesium, it has a charge of +1, and it has a charge of +1 because it lost its valence electron. It's a metal. It's far to the left on the periodic table. It can barely hold on to its electrons. But out here on the outside of the classroom, well, there we got a bunch of halogens. Now the halogens, very opposite to the metals, they have incredibly high electronegativities. So these guys all get a negative charge. And if you can see, there's a negative charge and a positive charge, and you guys know what happens when opposites get near each other. They attract. And that's basically what holds an ionic bond together, is this opposite the attraction between the opposite charges, like the positive and the negative. Are you guys picking up what I'm putting on there? Great. Now the other thing that you need to know is, well, how do you know if two atoms are going to do an ionic bond? Like, how do we know? How do we know if the metal is holding on so weakly and the non-metal is pulling so strongly? How do we know that there's enough difference in energy to rip an electron off? Because those electrons are there. They're kind of stuck there, and there's like protons in the nucleus holding on. Here's how. If the difference in electronegativity is greater than 1.7, then the bond's going to be ionic. And what I want you to dial in here is that it's going to be the difference between the two atoms. So what you need to do is you need to take two atoms that that are in question, and you go to table S and you look up their electronegativities, and you use the very complicated process of subtraction. And when you subtract the two or find the difference, if that difference is greater than 1.7, that means that one atom is strong enough to rip the electrons off and gobble them up. Okay, and that means you're going to have an ionic bond. So typically, also, because we're just starting out here, this is not like, this is your first chem class. So typically, the metals are going to be transferring one or more electrons to the nonmetal. So in other words, metals are going to lose electrons. Okay? Metals lose electrons. At least for us, when you have a metal and a nonmetal, we're always going to say that the metal is what's going to lose the electrons. The reason being, metals don't really hold on to their electrons very well. They typically have very low electronegativities, right? And I mean, it's one of the fundamental properties of metals is that they tend to have low electronegativities. And because of that, almost all metals are going to have a positive charge. And dude, look up on the periodic table of the elements. Almost all your metals have nothing but positive charges. Do you understand what I'm saying? So because of that, the nonmetals are going to be negative, right? Because if the metal lose and the nonmetal gains, that's how that works, okay? And the reason why they do this, right, like the fundamental like driving force is because they're going to get the electron configuration that is the most stable, right? So it's going to be the electron configuration of a noble gas, and the reason being is because that is super stable, right? They're going to have that like magical crazy 8. Right? That's the thing that all atoms want, because it makes them super happy. And then because the electrons are transferred and there's a charge, those difference in charges are what stick those ions together. Le voila, all is good. So quick review. How do you tell if so first of all, an ionic bond is a bond held together by ions. Well, how do you know if it's going to be an ionic bond even to start with? Well, you go look at the electronegativity. See if it's greater than 1.7, and if it is greater than 1.7, what that means is that metals are going to transfer their electrons to the nonmetals. So the metals will lose, the nonmetals will gain. The metals become positive, the nonmetals become negative. Both ions now have the electron configuration of a noble gas, which makes them super duper stable, and then they stick together because, opposites attract. Not bad, huh? So let's look at this. Let's look at this from like with what's going on with their electrons. So with sodium and chlorine, you just put these two elements near each other, and you will have what we call a vigorous reaction. And here's why. The sodium, right? The sodium has an electron configuration of 281. So this dude is going to have one valence electron. I'm just going to make it a plus just so we can see them apart. All right. And then chlorine will have 7. So I'll go 1, 2, 3, 4, 5, 6, 7. Now I used a plus for sodium and dots for chlorine just so we can see the difference, right? So we put these two things together, and it turns out that if we go to table S and look at the electronegativities, the difference is indeed greater than 1.7. So that indicates to us that like electrons are going to be transferred, they're going to be lost. And it's pretty easy to tell who's going to be losing and who's going to be gaining and why, even if you don't remember that sodium is a metal and therefore loses, and chlorine is a nonmetal and therefore it gains. Look, man, if you could just scrape off that one outer electron, there's 8 right there, and that is, man, that's fire right there. Really. And look at chlorine right there. Dude, if you could add just one more, that one's going to be 8. And again, that will be fire. So that's kind of why it happens, because it's super duper stable. So the chlorine gives up or transfers its electron over to the chlorine, and what we end up is sodium with a plus charge, chlorine with a minus charge, and look at these configurations. 8's all over. Woo! So this one, let me get my reference table here. 2-8. 2-8. This looks just like neon. And 288, period 3, that looks just like argon. Because, super crazy stable. So they like to ask you like what noble gas configuration, just so that you know that it's like unbelievably stable, these electron configurations for the ions. And then, now that we have the ions, they stick together because of their opposite charge. Do you guys get what I'm saying? And one of the things that we like to do, and it'll serve you well like in the future. When we do draw ions, what we're going to do is for the positive ones, you just put the symbol and then you put a charge. But for the negative ions, it is going to be very, very important that we put brackets around the ion, like that, and charge on the outside. And what that does is it walls off all of the electrons so that we know that these electrons are not being shared. This electron that came from the sodium now it's pure chlorine. It's all chlorine. It belongs to the chlorine. It's not being shared. And that will come in really handy later on. So again, our negatively charged ions are going to need to bracket. And the reason why we have a bracket is stupid. Because the bracket shows that the whole thing is an ion. You guys get what I'm saying? Yeah, they gave an old guy a camera. there we have it. Sodium chloride. It is a compound. And this word compound means zero charge, neutral. So all the pluses have to cancel all the minuses. And with this particular compound, it's pretty nice. It's just a +1 and a -1. So it's easy. And remember, the bracket shows that the whole thing is an ion. You will need to bracket off every single negative ion. We'll definitely see why later. Like at the end of this chapter, it becomes pretty gosh darn important. Otherwise, things just look totally chaotic. All right, so that's like how ionic things happen. So what are ionic things like? Well, the best thing that you could possibly lock into your brain is table salt. Because that is a very ionic thing, and everybody knows what table salt is like. So most ionic things, they are very, very hard. They are solid as can be. They are brittle. Now, brittle means that if you hit it or like with a hammer or something, it just crushes and shatters, right? So like you can crush it up pretty easy, like cement. I mean, cement's pretty hard, but it's brittle. It doesn't bend or anything. It just like cracks and shatters. You know what I mean? Also, high melting point, things like table salt. I have never seen table salt melt in a kitchen ever. Like, ever. I can't remember what the melting point of table salt is, but it's some ungodly huge number. Like, the cast iron skillets are going to melt before the salt will. Now, here's a little thing that's weird about ionic things. The solid does not conduct. Okay? It cannot conduct. And when I say conduct, I mean conduct electricity. However, if you melt an ionic substance, if you melt it, like make it into a liquid, it suddenly conducts electricity. Now, the reason being is that to conduct electricity, you have to have ions that can move around, which is why metal conducts electricity so well. They have those really, really super highly mobile valence electrons. So those electrons are mobile ions, and they can move just like all over the place. You guys get what I'm saying? So look at this table salt right here. Man, dude, you can just look at it, and dude, that stuff is like locked in place, man. Like look at that. So like this stuff, you can just look at it and know that like whatever is right here, it's stuck right there and it's not going anywhere. Does that make sense? However, once you melt it, these ions can float all over the place and go wherever they want once it's a liquid. But when it's a solid, remember way back in chapter 1, the particles are held in place, no conducting electricity. There you go. So solid does not conduct, but the melt does. And it forms an electrolyte solution in water. Now, you might be wondering to yourself, what does the word electrolyte mean? Because, it's in Gatorade, so it must be important, right? It's what plants want. So, an electrolyte is anything that conducts electricity when dissolved. That's a dot, by the way. But just don't touch. Don't judge. Stop it. So an electrolyte is anything that conducts electricity when you dissolve it in water. Got it? So like when Gatorade says, or Powerade, or whatever it is you like to drink, like, oh, it's loaded with electrolytes. All they're doing is adding a little bit of table salt and some potassium chloride in there. That's it. I mean, you can just get Kool-Aid and add salt to it. That's pretty much what Gatorade is. Also, ionic substances make the most beautiful geometric crystals. Geometric meaning like, dude, look at this thing. Look how pretty that thing is. That is table salt. That is making quite the nice, like, whoops, not you. Quite the nice little, like, square cube thing, whatever you want to call it. But that is about as geometric of a crystalline shape as you're ever going to see. And the reason being is because they kind of line up like positive, negative, positive, negative, positive, negative, positive. And so you got this big crystal, and then all of a sudden it lines up pretty beautifully. You got it? Now, this is another little, like, interesting thing about nature, because why would nature be, easy? As it turns out, not all things in nature are created exactly equal. So, everything's different. It's not like ionic, not ionic. There's like a million different like degrees in between. And the way that we can tell the difference, or like how ionic something is the difference in electronegativity. So if you have a greater difference in electronegativity, the more ionic the characteristics. So in other words, that means like it'll be harder. It'll shatter even more. It'll have an even higher melting point. The geometric crystals will be even more locked and intensely sharp. So if you have, for example, a difference in electronegativity of like 1.8, this will be less ionic. And if you have something way on the other scale that has a difference in electronegativity of like 3.9, this will be like way more ionic in characteristic, right? So this would be like crazy solid and like perfect, beautiful, sharp edged geometric crystals, whereas this one might be like hard, but you know, maybe you could bend it a little bit before it breaks, and maybe it won't exactly like shatter like into a million pieces, but it'll just like break off, you know. So it's like a million different like shades in between one or the other, as always, because I've never ever known nature to be just like simple and easy. And if you ever get there, let me know. Anyway, moving on. Oh, we're not moving on. We're all done. That makes me feel happy. So the two worksheets that we're going to work on for this are ionic bonds and losing and gaining electrons. So the ionic bonds, we are going to look at exactly what happens during an ionic bond. We're just going to kind of review all the things we did, but with like an example. And losing and gaining electrons, that's where we are going to go through and compare two atoms, look at them, look up the electronegativity, and see if we can tell if they will gain electrons, or I'm sorry, if they will lose electrons, in other words, if they will be transferred or not. Okay? All right, man. I hope you all had half as much fun as I did, and I also hope you have a great day. We'll see you on the flip side.